Hello, this is Psych. Welcome back to my channel. And today I actually have a special presentation for you. My student, Kate Schaefer, is going to talk to you about effect size. And at this point, will just hand it over to Kate.
Hi, my name is Kate. I am a student and an assessment consultant at James Madison University in the Center for Assessment and Research Studies. The topic of this video is an introduction to understanding effect size. Often when we make easy, everyday decisions, we simply rely on our own intuition. When a decision gets complicated, we may need more information than just our own experiences to come to a conclusion. What if you need to know which washing machine is going to last the longest, or which car has the best gas mileage? We may turn to research and statistics to investigate these types of questions further. Let's say our friend named Charlie wants to open a coffee shop. Charlie knows that both cold brew and iced coffee are very popular, but he isn't sure that they are equally popular. Opening day is approaching and he wants to make sure that he has enough of each type of coffee so that people get the best impression of his coffee shop. Should he prepare to have equal amounts of each? Or do a substantial amount of people drink more of one compared to the other? Should he be prepared to have unequal amounts of each? Charlie has a suspicion that more people may drink cold brew. He decides to survey a random group of people in the area. He asks them if they usually drink cold brew or iced coffee. After surveying 50 random people, he finds 30 people that like cold brew and 20 people that like iced coffee. Not only do more people seem to drink cold brew compared to iced coffee, but a substantial amount of people seem to drink more cold brew than iced coffee. Charlie says that his sample shows that 60% of people drink cold brew while 40% drink iced coffee. If this were a low-stakes situation, he could simply take the proportion of people that drink cold brew and the proportion of people that drink iced coffee and adjust the amount of coffee that he makes accordingly. But for argument's sake, let's say that this is a high-stakes situation. Charlie can only choose to make one type of coffee, cold brew or iced coffee. Does it matter which one he chooses? Will he lose 40% of his customers if he stops selling iced coffee? Charlie asks, what type of coffee is liked more, and what is the magnitude of this difference in liking? To answer this question, he conducts a second survey for this high-stakes situation. On this survey, he asks 50 people to rate how much they like cold brew and how much they like iced coffee. They rate their preference for each on a scale of 1 to 10, with 1 indicating no liking and 10 indicating the highest level of liking. He then gets a set of 50 responses for cold brew liking and 50 responses from the same people on their iced coffee liking. Charlie calculates an average score for each group and sees that on a scale of 1 to 10, the average cold brew liking in his sample is 6.5 and the average iced coffee liking in his sample is 6.1. He runs some analyses and finds that his data is normally distributed and satisfies assumptions to run his statistical analysis of choice, a t-test. He runs a repeated samples t-test and finds a statistically significant result. His p-value is less than 0.05. There is a statistically significant difference in the level of liking of cold brew and iced coffee, where cold brew seems to be preferred. But what does statistically significant mean? This is the probability of observing this value or greater when we assume that the results are due to chance. In Charlie's case, this value is the difference between the two groups. The p-value Charlie calculated was less than 0.05. He could say that there is a less than 5% chance of observing a difference in this data if, theoretically, a difference did not truly exist. The theory behind statistical significance may be difficult to interpret. Many who are new to statistics are introduced to the idea of statistical significance as the end-all or be-all for all of our research questions. However, Charlie hasn't fully answered his research question yet. he can only choose to serve cold brew or iced coffee. He now knows that there is a statistically significant difference between cold brew liking and iced coffee liking, but he also wants to know how large that difference is. This is where he should start to investigate practical significance. Obtaining an effect size will help him answer this question. Unlike statistical significance, like p-values, effect size can be interpreted in terms of strength or magnitude. How large is this difference in liking between cold brew and iced coffee? Is it meaningful and practically significant? We can graph this data to examine it visually. This graph has the frequency of a certain liking score on the y-axis and the level of liking on the x-axis, which ranges from 1 to 10. We can see that these frequencies form distributions for the cold brew group and the iced coffee group. We know from Charlie's analyses that they are normally distributed. The results from this survey show an average liking score of 6.5 for the cold brew group and an average liking score of 6.1 for the iced coffee group. Since the scale ranged from 1 to 10, we can say that most people indicated just above mid-level liking for both cold brew and iced coffee. Additionally, cold brew seems to be liked slightly more. When we look at the distribution, we see that overall the cold brew group sits a little higher than the iced coffee group along the x-axis. The peaks of the distributions represent the means of each group. Obtaining the effect size will tell Charlie if this mean difference is practically significant, given the spread of the data. There are various ways to calculate effect size. Here, Charlie could use Cohen's d to compare the two groups to determine if the differences in liking were practically significant. A Cohen's d value of 1 is equivalent to saying that the means differ by 1 standard deviation unit. It can be difficult to determine what a small, moderate, or large effect size is without really understanding what a standard deviation is. A standard deviation represents the spread of the data. It is a measure of how much the sample is varying from the mean. The majority of our data, about 66%, will fall within plus or minus 1 standard deviation units from the mean. Holding all other things constant, a large standard deviation will indicate a larger spread or more variability in the data compared to a small standard deviation. The units of Cohen's d are based off of a pooled standard deviation between the two groups being compared. The mean differences, as well as the standard deviations of the groups, factor in to the formula for Cohen's d. Let's look at this animation to see what different effect sizes look like. As effect size increases, the overlap between the distributions decreases. We can also change the standard deviation while holding the mean differences the same at 6.3. If we increase the standard deviation, we see that Cohen's d decreased from about 0.4 to about 0.3. It can be difficult to determine whether or not a certain effect size is large enough to be practically significant. Size classifications vary from discipline to discipline. They also vary from the type of effect size used. It is important to recognize that any interpretation of an effect size is relative to many factors. An effect size of 0.2 might be very small for one study, but large for another. Interpreting effect sizes requires an understanding of the discipline being studied, the type of effect size used, the instrument or survey used to collect the data, the spread of the data, such as the standard deviation and variability, as well as the number of data points or people surveyed. It is important at this point to emphasize that statistical significance does not have a bearing on effect size. There may be a statistically significant difference in our data with an effect size that is interpreted as practically non-significant. There may also be a non-statistically significant difference in our data that has a moderate to large effect size. This underlines the importance of reporting both values in our results. Let's look back at Charlie's study. He calculates Cohen's d to be 0.4. There is a 0.4 standard deviation difference between the mean liking of cold brew and the mean liking of iced coffee. This standard deviation is based on the pooled standard deviation between the two groups. Charlie might say that this is a small to moderate effect size based on what we know about Cohen's d and this field of study. There is a difference between what type of coffee people seem to like and that difference has some small to moderate practical significance. Now, let's put everything you know about these differences together to help Charlie decide which coffee to sell. There was a statistically significant difference between how much people like cold brew and how much they like iced coffee. People seem to like cold brew more. That difference has a small to moderate practical significance. When we look back at the distributions, we can see that the mean liking is above the midpoint on our 10-point scale for both groups. However, the average likability between the two coffees doesn't seem to differ dramatically. When we look back at the two distributions, we see that there is overlap between the two groups. Had the effect size been larger, there would have been less overlap. In this high-stakes situation, Charlie can only choose to sell cold brew or iced coffee. Knowing all this information from his study, we can help Charlie come to the decision to sell cold brew and stop selling iced coffee. We base this decision off of the statistically significant p-value he found and the small to moderate practical significance showed by Cohen's d. Recall that the first survey showed that 60% of people drank cold brew and 40% of people drank iced coffee. The second survey showed that Charlie conducted showed that most people still like both types of coffee, with only slight differences between the two. He can decide to only sell cold brew without worrying about a huge chunk of people stopping coming to his store if he doesn't have iced coffee. This example used Cohen's d, but there are other ways to calculate effect size. Eta squared in ANOVA is a form of effect size. Correlations and squared correlations also represent the magnitude of what our hypotheses can explain. The value of a correlation can be directly interpreted in terms of strength and direction of a relationship. Remember, statistical significance does not always mean practical significance. Effect sizes should be reported and interpreted to get a better picture of what our data actually means. I hope this was a helpful way to be introduced to effect size and practical significance.